Okay, I want to continue on from yesterday. Now we're having two full chapters on bonding. I mean, it's a big, big topic. The dry lab today is going to be practice. Gee. Maybe a short lecture today. It's going to be practicing Lewis structures. Now, some of you may remember that really well, and others may go, wow, I need lots of practice. So you can vary it from there, okay? And we're going to be doing the dry lab in here also. All right. Yesterday we talked about these numbers here. Talked about the delta. God. The delta En being 0, less than 0.4, less than 2. And this is a nice diagram to show that. However, I'm going to differentiate 0 versus 0 to 4, 0 to 0.4, okay? So at 0, so when delta electronegativity is equal to 0, we're going to call that a pure covalent. If it's in other words, if it's between this area, I'm going to call that a non-polar. Okay, if it's 0.4 or greater, yeah.
So it's 0.4 unless it's non-polar covalent or polar.
Remember I said there was a big gray area?
Yes.
It's just they just put a stake in the ground. Some textbooks say 0.5. So if I ever give you a question like this, it won't be 0.4. It'll be just because you can make a case either way. You know. Some of them say greater than or equal to 0.4 or 0.5. Some say greater than 0.4 or 0.5. So in one case they include it, in one case they don't. And the point is, it goes from 0 to 3 and beyond. It's a continuum. It's a pure continuum. There's no areas that are devoid of some kind of relationship. So they just said, well, if it's 0.4 or less, it's starting to get polar character. After that, it's considered a polar covalent bond, still sharing, but totally unequal sharing. And then where it gets to the point where it's so unevenly shared, it becomes an ionic bond. So this is an important chart to understand. Another point here is notice this little squiggly minus sign, squiggly positive sign. Who knows what that means? Yeah. I'm sorry, say it? No. Has anyone had, yeah.
I believe it's a lowercase delta.
Right, and so what does that indicate? That's right, exactly what it is. Lowercase delta, uppercase delta. Yeah. Yes and no, but whenever you see that little, sometimes you'll see that. Sometimes you'll see that basically it's a partial delta, which is weird. And when you take differential equations, you're going to have something called a partial differential equation. And they use only these. So that is a D. Okay. So this means it's not a full delta, partial delta. Okay. So so this then here is not a full positive sign. It is a partial positive sign or negative sign. If this was a plane plus or plane minus, it would be an ionic bond. So when this area here, you're becoming more and more ionic character. In other words, that sharing is becoming more and more unequal. Unequal is a key word here, okay? And they differentiate that with, no pun intended, partial delta. And you'll see that when you get into more advanced math. You'll see it quite a bit, actually. Okay, so this then is okay. Now, whenever you have this imbalance of charge, that's considered a dipole. Di meaning two, pole meaning polarity. Okay. So dipoles are important when we're talking about the overall polarity of a molecule. Dipoles also are vectors. Who's heard of vectors? Okay, third of you or so. Okay, the important thing about a vector what are the two properties of a vector? Yeah.
Direction and magnitude.
Yes, okay, so a vector has a direction. And then it has a quantity or magnitude. Now, vectors can cancel each other out. A force. When you get into physics, you're going to talk a lot about forces, and they're all vectors. And vectors, if the forces are, directions are opposing one another, and the magnitude is the same, they will absolutely cancel each other out. If they're opposing, but the magnitude is not the same, it'll partially cancel the other one out. Okay, but the important thing is it's got direction besides quantity or magnitude. So when we get into determining whether a molecule has polarity or not, we have to look at all the little bonds that have a dipole in them. And do all those cancel out? Let me give you an example. Carbon dioxide. Let's look at the two bonds that we have there. We have a C double bonded O and a C double bonded O. Okay, so let's look at first the change in electronegativity between the two. Okay, I put a chart here that's easier to read. Okay, carbon's 2.5, oxygen's 3.5. So we've got carbon, oxygen. Okay, so in our chart, 1.0 means is that a pure covalent, non-polar covalent, polar covalent, or ionic? Polar covalent. Okay, polar covalents have a dipole. Even non-polar covalents have a diminishing dipole till it gets down to pure. There's no dipole. Okay, so we have now, which is more electronegative, the oxygen or the carbon? Oxygen is more electronegative. Okay, it's 3.5. Carbon is 2.5. Okay, so we're going to draw a dipole using an arrow. Okay. So for the right side double bonded O, oxygen has higher electronegativity, carbon has less. That means our arrow is going to point to the one with more electronegativity. Okay, and that looks like a plus. So remember the tail that looks like a plus points to the one with less electronegativity. Now we have a dipole here that's exactly the same as this, only it's exactly opposite. Because if we just look at that one right side carbon double bonded O, we're going to say that is a pretty polar covalent bond, right? However, this side, it's got the same quantity, 1.0, but the direction is absolutely opposite. So the first thing to look at when vectors, you look at the quantity first, then you look at direction. Now, when you get into physics, you're actually going to take that vector apart into its X, Y, and Z directions, because it may cancel on the X-axis, but not on the Y-axis. Or it may cancel on the Z and the X, but not the Y. So you've got to add up all those components to see what the net vector is, okay? So the net vector are all the forces together vectorially added up. Okay, so because these are 180 apart, they're going to cancel. And since the quantities are the same, the dipole is totally going away. Okay, so the net vector is everything together. So in the case of carbon dioxide, is that now overall, CO2, is it a polar molecule or a non-polar molecule? Hmm?
That's above 0.4, so that would be 4.
Okay, these quantities are the same. Directions are exactly opposite. So this one cancels this one out. So carbon dioxide is non-polar because it has a net vector of 0, both directionally and quantitatively, or magnitude, yeah.
Is it like how you do the math? So like the tail of the second vector is place the first to 0.
Yeah, think of it graphically that way, yeah. The problem is what about when you get it like this? Then you got to look at the X and Y components. Because sometimes 2 of the components cancel out, but not the other one. So the net is a new vector in a different direction with a different quantity. I'm going to show you that in a minute. Yeah. From an electronegativity chart that I would always give you, And that's what the one the book uses is 3-dimensional, which is, in my opinion, harder to read. This is the one I pass out. This is the one the book uses. This one here. It's just, it's nice as a visual, but clumsy to use. So I'll always give you that, or if it's a take-home test, you'll have access to it. Okay. Okay, now when we get into solutions, we're going to find that there are properties of solutions. And there's a very generic term called likes dissolve likes. And it's a polarity concept. So nonpolar things dissolve nonpolar things. Polar things dissolve polar things. So driving down the road and they just newly oiled a road. I just washed my truck. Guess what? And it's a white truck. What color is road oil? Black. So guess what? I got all this stupid black oil on my truck. So I get to my apartment, I get out a hose, nice cold water, except for today, it's probably warm. Spray it, nothing happens. It doesn't wash off the oil. Why? Water does not like oil, so it doesn't dissolve oil. Remember, like dissolves like. So I ran inside and got some vegetable oil and smeared it, squirted it all over that road oil, and it came off. Why? Like dissolves like. Oil dissolves oil. And then, of course, I had vegetable oil and get off, which is easier than the black stuff. Then I just use some soap. Now, soap is an interesting concept. It's called an emulsifier. Emulsifiers work by having the molecule have a polar part and a non-polar part on one molecule. Soap is an example. Lecithin is an example. Detergent's an example. Frequently in my organic class, I'll give someone a molecule and say, is this an emulsifier or not? And then they have to identify all the functional groups, determine if those are polar functional groups or non-polar functional groups, and then make a decision whether it's an emulsifier or not. So if I had an emulsifier, like soap, I could have used it directly on the oil because the emulsifier has a non-polar part sticking to the oil and a polar part sticking to the water. And so they come off together. That's why when you put a greasy pan in the sink and you pour water on it, the grease just floats. And you squish in some soap, gosh, it all comes off, goes down the drain. So anyway, so polarity-wise, like dissolves like. Okay, remember that. It'll do you real good in everyday life. Okay, let's look at one more molecule. Okay, is water polar or non-polar? Let's look at taking it apart, okay? Now, water is shaped like this, not that. In our next unit, we're going to talk about that quite a bit. But let's just assume that the lower one is correct, and it is correct. But this is for this little talk here. Okay, so we've got an OH bond. Okay, so let's find the delta EN on that. Oxygen is 3.5, we just looked it up. And hydrogen, I think is 1.1, let me see here, 2.1. So we have a 1.4. That's pretty polar. Okay, so we have a vector now on one leg, and the vector on the other side is the same thing. Now remember, it points to the one the most electronegative between the two. So let's look at this more closely now here. So we have an X and Y parts of the vector. This part, the X part of this vector goes this direction. This part goes this direction. The Y parts both go up. So the X parts cancel because the magnitude and the direction are equal but opposite. The Y parts add because they are going in the same direction. So we have a quantity plus a quantity together equals the net vector. So the net vector is going to be going in the cancel part of the X's. So these two cancel, meaning that the result is 0. And these two, because they're going in the same direction, add together. So we have a net vector of going up, straight, and a combination of each Y component. So the net vector looks like this. Okay, so you've got to look at the net between all the forces before you can decide whether the overall molecule is polar or nonpolar. So what do you think? Huh? Okay. It's hydrogen bonded between the molecules, not within the. So we have intra and inter bonding. Now we're going to cover a whole topic on intramolecular forces, which has to do with hydrogen bonding, is one example of that. So we're talking about internal bonding. Okay, good point to bring up though. Okay, so what about water? Is it polar or nonpolar? Polar, because we have a net polarity, a net dipole that's strong in one direction only. That means it's polar. Okay, so we found with carbon dioxide, we had two vectors that individually are polar, but because they were exactly the opposite, they cancel. So the net is 0 on carbon dioxide, even though it's got two polar dipoles. They're opposing, so they go away. Water, because the directions aren't opposite. Only the X parts are opposite. The Y parts are not opposite. So the Y parts tend to add. So we have a big net vector there. Yeah.
What do you, or how do you know what your Y value is?
Well, it depends on a trigonometric relationship.
Okay.
Okay, so the value of Y is cosine of 1.4. And the value of X is the sine of 1.4.
So like for this class,
This class,
I know you like will probably have to stuff. So then how did you know that is it just because of the shape of the water that we know that?
Yeah, I didn't give any angles or anything like that. Yeah.
So you're going to tell us that that's 4 if we have a centric?
A 4?
Yeah, because you're just saying that cosine and sine is what gets you the y values, which, oh, those are y's, not 4s. Huh. Okay, I was very confused.
Do you see where the 1.4 comes in?
Yes, I do.
Okay.
I thought that meant
And
that
don't
the y's
worry.
were 4.
Yeah, don't worry. You're going to do this a lot in physics. Oh my God. When you get to the first major unit in physics it's called statics. And you do that a lot. A lot. You have drag forces, you have acceleration forces, you've got forces out the yin yang. Who in here has had physics? Okay, is that a true statement? Oh, it's like, so this stuff is like barf easy. It really is. Okay. So for our class, the main thing is it's a qualitative argument. Quantitatively, that's the way you do it. So you have to know the angle. And actually, you can approximate the angle. And our next subunit is on something called VSEPR, which is valence shell electron pair repulsion. And you actually calculate the angle.
So since they're going in the same direction, how do we know that's 4?
When we get the vector apart, we've got one's we have, I'm so sorry. We have 2 components going in the same direction. 2 directions opposing each other. So the ones opposing go away, assuming the quantity is the same.
Yeah.
And it is the same because there's 1.4 in both of them. But these are going in the same direction. So they add. So you end up with a net vector. If everything is going opposite, then everything cancels out. And then it's nonpolar. So then there's no net vector.
Okay.
Think about that. And during our...
So it's basically like, because is the net vector just checking your delta En value?
Yeah, and the net vector is kind of a qualitative thing.
Okay.
You can make it quantitative, but not in this class. You just have to kind of look at it and say, okay, this is 1.4, 1.4. It's kind of pointing this way anyway, if you kind of think of it as a head of an arrow.
Yeah.
Okay, but this part, the horizontal parts, cancel.
Yeah.
But these parts add together.
Okay.
And so all you need to say is, yes, it's polar.
Okay.
And does it make sense why?
So you would use the values that add together, and then you'd use your.
You don't even have to add the values together because you don't know what it is unless you took the sine or cosine of the quantity.
But what if we have our delta ENs? Isn't that your vector?
Yeah, that's the quantity of the vector. Okay, so but each component is it's a subcomponent of 1.4.
Okay.
Unless you know the angle, you can't figure what the subcomponent is.
Okay.
Unless I gave you the angle and you were really nerdy that day, you go calculate it.
Okay, so since they add, sorry, I'm just confused. How do we know that because they add together, they're polar? I don't get that.
The part, think of them in parts though, an X and a Y value. Okay, take them apart, okay?
I get the X's cancel, but how do we know that the Y's together are polar?
Okay, so if we normally in physics, we go like this. So vectors can add together algebraically. So notice the X vectors that are subpart are going in the opposite direction. And because the 1.4 is the same, that means the quantity is the same. So they go away. Okay, the Y value, notice that they're going in the same direction. So they're going to add because they're going in the same direction. So we know now that the net is going to be going basically in that Y direction. And it's not 0 because they didn't cancel, they're adding.
Yes, I get that. But how do we, I'll ask you later. Never mind.
No, why don't we just,
Well, so I get that the Y's add together, they're going in the same direction, but how do you know going in the same direction means polar?
because you end up with a net vector.
Okay.
This vector has no x values, notice? It's totally going straight up.
Okay,
All it's got is the y parts of the vector.
yes.
So when those add together, the new combined vectors goes up only,
Okay,
has no side parts. The sides, the x parts cancel.
okay,
So if you get anything at all, that means you have a dipole.
okay.
Dipoles are polar.
Got it. That's it.
And that's the difference between the origination of the dipole, the delta ENs determines how strong that dipole is.
Okay,
So if the net is 0.4 or less, it's not very strong. And you can't calculate the net because you have to do the trigonometric functions to get the x and y components.
Okay.
Main thing now is just look at it. And I'm going to show you a tricky way when you look at a molecule to determine if it's polar overall or not. A real easy way. And it's going to depend on your common sense experience in life, which will determine. And it really works. Yeah.
So because they're going in the same direction, they just cancel. And then you're not.
No, same direction, but opposite. And the quantities are the same.
Okay.
The
so
quantities
it's not
have
gonna
to be the same. Excuse me?
It's not going to be 2.8. You're not adding them together like you did with carbon dioxide. It's going to be just
No,
cancel.
no, because that's not an angle,
Oh,
only part of it.
because we don't know. Okay.
Yeah. Then you do the angle with the trigonometric deal and all that stuff. Okay. All right. So bottom line is, it's very important in your future chemistry is to be able to look at a molecule and say, oh, it's nonpolar or polar. Particularly in OChem, particularly in biochemistry. It's more quantitative in 1A and 1B than OChem, but you need to be able to get comfortable with, gosh, this is really polar or this is really non-polar. Let me give you another medical example. When I was 4 years old, I had extreme asthma, which probably is why I'm coughing a lot now. And I lived in Texas, and in the 50s, this was the late 50s, this is the mid 50s, the only cure, and it wasn't a cure, it was more of a treatment for asthma, was vitamin B12 shots. And they gave them to you in your butt, biggest clump of muscle. And because they were non-polar, my blood, what's blood mostly made of? Water. So blood is polar. So the only way I can move that vitamin B12 shot from my butt to the rest of my body is via my blood. So if the vitamin B12 is polar, the blood can pick it up and move it around. But guess what? It's not polar, or non-polar. So it sat there in my butt for 3 hours and I couldn't walk for 3 hours. I remember my dad would take me to, this is, you remember things when you're little. Now this was 68 years ago, okay? I still remember this. My dad would take me to Woolworths, which is long gone, and he'd buy me these little chicks, little cheapy little things you get at Easter all the time, every time I get a shot. So I remember that so much. Peeps, yeah, exactly. And so they improved vitamin B12 by putting polar functional groups on it. And that was a take-home question on one of my OChem classes. So I gave him the structure of vitamin B12 and I said, how would you make this more motile in the blood? In other words, motility is the ability to move stuff around in your body. So how would you make this vitamin B12 molecule more motile? Okay, they would look at the functional groups and then chemically change the functional group to be more polar. And then have the reactions and all the junk. But it's a real life example. So this whole thing in polarity in medicine is really a big deal. You'll notice a lot of your drugs will have, they'll say chloride on them at the end, or sulfate and stuff. The reason for that is because most drugs are very nonpolar. With that sulfate or chloride hung on there, it makes it polar. And high motility in the blood. So it's really a good concept to get down. Okay, so because water has a net vector, it's polar. And that net vector is actually pretty good size. So water is very, very polar. And one of the things about water, because it's polar, when it gets near another molecule, it's attracted to it. So dipoles like to attract other dipoles, just like magnets like to attract other magnets. So that's why with water, they say it has hydrogen bonding, because from one molecule of water to the next, the big dipole from the water attracts the big dipole in the other one, and they attract. And water is a very special molecule in this world. There's a lot of things weird about water. It's a very high heat capacity. It has a very high hydrogen bonding. And because of that, when it cools down to 4 degrees Celsius, when you go lower than that, instead of getting more compact, it gets bigger. That's why ice floats. It's because at 4 degrees, because of the hydrogen bonding, it actually increases in size, hence it floats. Think of the world without ice floating. We wouldn't have fish, or at least the kind of fish that are today. A lot of amphibians wouldn't be around. Also, water expanding causes erosion in the mountains. If you go up into the mountains, into the big granite areas, you'll see these slabs of granite that are about to kind of slice off. That's because water gets in there, and when it freezes, it expands. So it makes a little bitty crack. And the crack each year gets bigger and bigger and bigger, and then all of a sudden it slides off. If you're in a coal country, like I was living in Washington, we have, they're always filling cracks in the roads. The reason why they're filling cracks in the roads is to keep the water from going into the asphalt and expanding. And it's so bad in Alaska, they call them, there's heaves in the road, swells. Anyone lived in Alaska? It's very dramatic up there because they have such long winters, and yeah. And North Dakota probably has a, yeah, and right. And in fact, in North Dakota, Alaska, Juneau, for example, is a lot warmer than North Dakota. Fairbanks is probably more like North Dakota because Anchorage is right by the water. So it has a tempering effect. But Fairbanks and probably the whole state of North Dakota are very similar. Oh, yeah. Yeah. I was up in Alaska once in the bush in January, and it was minus 80 because of the wind chill. It was, yeah. Yeah. And what do they call the swells in the road? They call them frost swells or something like that? Or, but you know what I'm talking about, right? Yeah. Yeah. The only fix is fixing the cracks in the road. And, you know, that requires, you know, maintenance and all that good stuff. So the more remote the road is, it gets less fixed. So water is really special. It's really a cool chemical. All right. Now, there's something called percent ionic character. Percent ionic character is really basically how strong is the dipole. If the delta En is big, then you have a high percent ionic character. And conversely, if it's small, you have a low ionic character or more non-polar character. Okay, so writing Lewis structures. There are two ways to do these. And one of the things that I mentioned yesterday, if we're looking at period 2 molecules, starting at now, Lewis structures, again, I want to reiterate, are valence electrons only. The core electrons do not come into play. So if we were looking at the valence electrons on, this is period 2. Okay, lithium has 1, okay. Now with Lewis structures, we frequently talk about, we don't talk too much about these. Mostly the focus is here. Now the anomaly here is carbon. Carbon is a definite anomaly. Because carbon says, the way it's written there, says it has 4 singleton electrons. Let's do the electronic configuration via orbitals for carbon. Okay, carbon's got 2s2, 2p2, right? So looking at that configuration, how many singleton electrons are there? 2. How many does that have? 4. So something's going on with carbon. Now, let me explain what's going on with carbon. It's called bond hybridization. Okay, so that's what it looks like from an energy perspective. Remember that when we were filling in the energy chart. So the s electrons are more stable than the p electrons. So they fill first, and then leftovers go into the less stable orbitals left over. Okay, which is that there, right? Okay, let's look now at that's what Lewis dot carbon looks like. It has 4 singletons, not 2. So what happens is, notice this line is supposed to be between these 2. So what we've done is we've increased these 2 electrons stability-wise or instability-wise. Okay. So they are not as stable anymore. And these two we've brought down, so they're more stable. Okay, so we've destabilized 2 and stabilized 2 at the same time. So we get a degenerate. Remember, degenerate in terms of orbital means they're the same energy level. So we have a degenerate 4 equivalent orbitals. Now from experimental value, this works, this doesn't. Let me show you. That's the formula for methane. Okay. If we use the original electronic configuration like this, this would be the formula. Because we only have 2 singletons. The singleton electrons are the only ones that can bond. This guy has 4 singletons, meaning 4 bonds. Okay, and that's called bond hybridization. Is basically we've hybridized this bond and hybridized these 3 bonds. Okay, that's why carbon has got 4 singletons. Silicone underneath carbon has got the same thing. So carbon undergoes bond hybridization. This is a big deal in organic chemistry because guess what? Organic stuff is full of carbon. And not only that, you've got 3 types of bond carbon hybridization for carbon. And that's why there are single, double, and triple bonds with carbon. It's because you've got bond hybridization going on. Yeah.
Where would that new like subshell, because it has 4 orbitals, where does that, like, how does that work? Because there is no, we have like 1, 3, 5, and 7 orbitals. So where does the 4, like, how does that work?
It hybridizes the S and the P's.
Okay.
Okay. So what you call those, instead of an S or a P, we call an Sp3.
Okay.
Okay, so an Sp3 hybridized bond is composed of an S and 3 P's together. So this would be a 2S subshell, a 2P subshell. This is an Sp3 subshell. Yeah.
Writing out the electron or the electron configuration for carbon, should we put Sp3 instead of like?
Yes. Yeah. When you look it up, well, actually, interestingly, if you look it up, it'll be this here, because carbon by itself doesn't hybridize, only when it forms a bond. So if you look up, which is weird, some books will mention this. Most of the time they won't. They'll say 2s2, 2p2. But the reason why the bond forms, though, is because of the hybridization. So only after the fact you get this going on. Okay, so when you write a Lewis structure, you've got to know these guys. And the only one that's odd is carbon. All the others, you know, this one's got, you do this structure here like this, you'll see the S's and the 3p singletons. The S's and the 3 Ps, the S's and the 3 Ps, S's and the 3 Ps, except for carbon. Okay. Now, to make a bond, remember we talked about how many electrons can be in an orbital. It's 2. So whenever you have 2 electrons in the same orbital, it's considered a bond if you're attaching 2 atoms together. If you already have 2 electrons in an orbit, then it stays by itself because it cannot bond anymore unless it's that special case of the coordinate covalent bond. Remember when we have an atom like hydrogen plus, it has no electrons, it can then bond to a full orbital. This happens with nitrogen as well. When you take NH3 and put it in water, it forms ammonium hydroxide. And the same deal forms. Okay, so now the official way to do Lewis diagrams is you count the total number of valence electrons, not core. Valence only. Okay, so in this case, we have 8 valence electrons. So step 1, hydrogen and the halogens are considered terminal atoms. That means they always go at ends because they only have 1 free electron. So terminal atoms always go at the end. So we have a total of 8 valence electrons. Everyone see how we got 8? Okay, step 1 is to take the most complex of the atoms, not counting terminal ones. And since we only have terminal atoms, except for the carbon, then carbon's got to be in the middle. Okay, and then you surround it with terminal ions. Okay, so, and then you start with making a bond between all of them. And how many electrons are required for 1 bond? 2. Okay, so we're going to need 2 there, 2 there, 2 there, 2 there. How many is that electrons? 8. And how many valence electrons do we have? 8. So that's now going to be now, every time you have a bond, you can replace it with a solid line. So that's the Lewis structure for carbon. And one of the problems with Lewis structures is they're 2-dimensional. Methane is not 2-dimensional. So later on in the century, they had to modify that. Yeah.
Is that what you use, like that little triangle, or like a shaded triangle? You know what I'm saying? Like with the bonds you would draw, like kind of like that, or like this, and you fill it in to show that one.
Yes.
Yeah. Okay.
Yeah. That's one goes in and one goes out.
Yeah.
And then the rest are in the plane of the paper.
Okay. Yeah. So would you use that then, or?
Yeah, so you have to figure out which goes out and which goes in.
Okay.
So in the case of that, this is tetrahedral.
Okay.
It looks like a pyramid as opposed to flat.
Okay, cool.
Yeah, and to designate that, you do it like that.
Mhm. Okay. Thank you.
Okay, so that's the Lewis diagram. Now, I'm not saying that's an accurate because it's 2D, not 3D. Okay, are there any questions about, that's probably the simplest example of a Lewis structure. Everyone okay with that? Let's look at carbon dioxide. We do a Lewis structure there. Well, how many, first of all, how many valence electrons total do we have? Oxygen has 6. There's 2 of them, so that's 12. Carbon has 4, so that's 16 total. And again, these are valence electrons, not total electrons, because the core electrons don't participate in Lewis structures. Okay, so so you put the less electronegative one in the middle. So, okay, oxygen is more electronegative than carbon. You're going to put the carbon in the middle. First thing we're going to do is we're going to bond carbon and oxygen. Okay, that's going to take up 2 electrons, right? Now, when you're putting electrons around these atoms, we have 2 guiding principles. To make a legal Lewis structure, you've got to abide by both 1 and 2, and in no particular order. Okay, we have to have a full shell per atom when we're all done. We have to have the correct number of bonds between the 2 atoms. These both have to be fulfilled. Okay, so okay, so that's the number of bonds per specific atom. Carbon's 4, nitrogen's 3, oxygen's 2, all the halogens are 1, and the noble gases are 0. And then boron is 3. Okay. And then hydrogen is also 1. So let's start putting some electrons in. Now, oxygen only has 2 shared electrons. How many electrons does oxygen need to fulfill its full shell? It's got 2 now. How many more does it need? This is advanced math. 8 minus 2 is 6, because 6 and 2 is 8. Okay, so oxygen, each one needs 6 additional electrons, right? Okay, so let's just slap them around here. Okay, that's 6 more. 6 more. Okay, so we've used 12. We have 4 electrons left. Okay, so oxygen's fulfilled in its full shell. What is not fulfilled with oxygen? How many bonds does this reflect right now? 1. We need 2 bonds to oxygen all the time. Okay, same with this one here. What about carbon? Carbon's all messed up. It doesn't have a full shell and it doesn't have enough bonds. So those 4 electrons are going to fulfill both of those if we want a legal structure. Okay, well, one way to do this is to put like that, okay? So that gives carbon 8 electrons now. Okay, and it's got 2 bonds. So the bond number is messed up. Oxygen's got 8 electrons, but only 1 bond. 1 bond. So we need to move those electrons around to fulfill both requirements. Okay, instead of putting them here, remember now, electrons are shared. What if we put them there? Okay, let's look at the rules now. Okay, how many electrons? 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. 2, 4, 6, 8. Okay, carbon's in a good place. Problem with carbon, though, how many bonds do we need for carbon? 4. We have 1, 2, 3, 4. Okay, double bond is just that. Double bond counts as 2 bonds, requires 4 shared electrons. What are we going to do about oxygen? So oxygen's got 2, 4, 6, 10. Okay, let's count valence electrons again. Okay, oxygen has 6 times 2 is 12, plus carbon's 4, so that's 16. So we counted valence electrons correctly. So how are we going to modify? And do we have 16 electrons here? We have 6, and 6 is 12, plus 8 is how many? 20. Too many electrons. Okay, so everyone see how we have too many electrons? We have 20 there, not 16. So we have to eliminate 4 of them to get down to 16. Which 4 are we going to eliminate? Oxygens. Okay, if we get rid of those, that's what we're left with. Now, let's count electrons now and make sure we have, okay, we have 8, 4 is 12, and 4 is 16, okay? Okay, we need to look at full shells. Oxygen has 8, carbon has 8, oxygen has 8. Bonding, okay, oxygen needs 2 bonds, 2 bonds, 2 bonds. Carbon needs 4 bonds, 2 and 2 is 4. So this is a legal Lewis structure. Remember, it's got to fulfill both of those requirements. So now we can fill it in with we're going to see tomorrow when we get into Vesper theory that it's a linear molecule. Okay. So you count up your total valence electrons, and then you start fulfilling the requirements for all the interior atoms. They have to have, full shell, whether it's 2 or 8, 2 for hydrogen, 8 for everything else. Gonna make sure the number of bonds is correct. Carbon's 4, 3, 2, 1, 0. Okay. All right, so does this make, are there any questions about this? Now, I know some of you have already had this in class before, so this should be a review. For the ones where this is review, is this the way you learned how to do it? I'm seeing none. Does anyone learn it differently? Because in my intro class, I teach it a little differently. And we don't start with counting valence electrons, we do it a little differently. Okay. All right, so let's try another one here. Let me tell you a story about formic acid. This was this was easy for me to say. This was discovered. An interesting story. There was a chemist, and his son was very deviant. So one day his dad came out and he was boiling a bunch of ants in water, red ants. And of course, you know, he was reprimanded. And his father analyzed the leftover liquid. And it ended up being this. And when you get bitten by a red ant, this is what it injects in you, formic acid. And who understands Latin? Anyone in here understand Latin? Okay. ¿Cómo se dice in Latino ant? What? Sorry. What is ant in Latin? Okay, it's forma. It's ant in Latin. And because of acid, that's what I ended up calling it formic acid. It's kind of an interesting story. Hopefully the kid grew up and changes deviant behavior. But anyway. Okay, so go ahead and do the Lewis structure for formic acid. Okay, let's change the formula. That's CH2O2. This will be an intro into our lab. And there's probably a alternate legal structure as well. With Lewis structures, you can have alternate structures that fulfill the two rules, the full shell rule and the number of bonds rule. So there are two ways to do this. Did you bring your lab packet?
Yeah.
Yeah, you'll see it's the next lab, whatever the number is. I think it's lab 12, isn't it? What number is this lab? Is it 12? 12, yeah. Yeah. So you can, if you've had this before in the past, then you feel comfortable with it, you can do it at home, or you can do it here, I like black backgrounds. Yeah, your eyes, with it totally white, your eyes focus on the white, and then the black lettering is less noticeable when you reverse it though. Your eyes focus on the black and opens up your iris, and then the white stuff really shows. Yeah. Now, when I was at IBM, this is back in the 80s, I was a publishing specialist, and we were the first company to actually talk about having a black background. Everyone's going, oh, that's so dark and not. But physiology-wise, it's much better for your person. So ever since then, black backgrounds for me. This making sense? Have you had this before? Oh, good. Oh, cool. I'm going to end this.